Magnet notes. A field force is a force that can act on an object without touching it. There's three different types of fields. There's a gravity field, an electric field, and a magnetic field. Magnetic field has a symbol capital B. It's measured in units of Teslas, and they're pretty similar to the electric fields. They follow the same rules. Opposite poles attract, like poles repel. And they have field lines. The field lines go from north to south. Remember, the electric field lines go from plus to minus. Where the field lines are concentrated, where they're closest together, is where that field is going to be the strongest, or where the force is going to be the strongest. On a magnet, that's always at the poles. Where the field lines are spread farthest apart, that's where it's going to be the weakest. On a magnet, that's in the center of the magnet. For the electric field, the field lines show the direction of force on a positive charge particle. If I put a positive charge right here, it will be attracted to the negative and it will follow this path. For the magnetic field lines, they show the direction that a compass would point. A compass always lines itself up with the magnetic field lines. The red side of the compass is the north end of the compass needle, and it always points towards the South Pole. What that means for the Earth is, in order for a compass to line up with the Earth's field and point north, the North Pole is actually a South Pole. We call this the South Magnetic Pole, and we call this the geographic North Pole. Magnetic fields are different from electric fields in several ways. We can have a positive point charge or a negative point charge, but you cannot have a North Pole. The North and South poles always have to be in pairs for magnets. In fact, if you break a magnet into smaller and smaller pieces, there's always a north and south side of the small pieces, even if they're really small fragments. Magnetic fields are related to electricity. It turns out if we run a current through a wire, it creates a magnetic field that circles the wire. That field is perpendicular to the current. Looking at the example here, we have a current going through a wire, and because that current's moving, it makes a magnetic field around there, and that magnetic field basically makes the wire a magnet, and that magnet can interact with another magnet and repel. If I reverse the current, that means I'm going to reverse the magnetic field, and then the two magnets will repel each other. Looking at the drawing here, the current is coming outwards, the field is going to the right, and the force is going up. Notice that these three things, the force, the field, and the current, are all perpendicular to each other. This wire carrying current in the field is going to feel an upward force. We can calculate the strength of that force with F equals L times I times B. L is the length of the wire that is in the field. We wouldn't count this length of wire because that's not in the field. You'd just be using this length that's inside the field times the current times the magnetic field. Remember, B is the new symbol for magnetic field. It turns out that the I and the B need to be perpendicular to each other in order for there to be a force. So if your wire or current is going at an angle, we would have to draw a triangle and find the perpendicular side. Oftentimes that's the sine side of the triangle, although I will warn you to watch out on the AP test. They will purposely give you the angle on the wrong side to catch who's trying to just plug numbers into formulas and who's actually paying attention. So substituting the I into the formula here, we get L times I times B times the sine of theta. Math review. Formula for work is force times distance. This is a dot product, which means the force and distance have to be parallel to each other in order to interact. Our force formula is a cross product, which means they have to be perpendicular to each other to interact. Looking at the units here, we have meters, amps, and Teslas. A Tesla breaks down to a Newton per amp times meter. All these units need to be memorized, and the easy way to memorize this one is looking at this formula. We have meters times amperes, and those two have to cancel out. That's why they're in the denominator. And after we multiply all three of them, it has to be newtons because we're finding force, so the newtons has to be in the numerator. So ampere breaks down to a coulomb per second. Did I mention you have to have all these units memorized? We're going to have a quiz on these in the future. the very near future. All right, so looking at the coulombs and the meters here, if I switch places with them, coulomb is the unit for charge, and of course meters per second is velocity, which brings us to our last formula today. Q is a charged particle that's moving at a constant speed in a magnetic field. So that is going to also feel a force from that field. And the V and the B have to be perpendicular, so the complete formula is QVB sine theta. All right, checking your notes, make sure you got everything.